This video will cover section 9.1, sequences and series. The objectives for this last section are to use sequence notation to write the terms of sequences, use factorial notation, use summation notation to write sums, find the sums of series, use sequences and series to model and solve real-life problems. Sequences. In mathematics, the word sequence in English is used in much the same way as in ordinary English. Saying that a collection is listed in sequence means that it is order. So that it has a first member or a first term, a second member, a third member, and so on until the last. Some sequences, we know which one is the last term or member, and others, as you could see here, we just don't know where they stop. So mathematically, you can think of a sequence as a function whose domain is the set of positive integers. So if we had f of 1, instead of we use this notation for functions, with sequences we will use a sub 1, for example, to denote the first term. And in this case, for this sequence, it happens to be number 1. So if I ask you what is a sub 3, it will be the third member, which will be number 3. Rather than using function notation, however, sequences are usually written using the subscript, as I showed you before. And you could also see that here in the definition. So in this case, since we don't know what the last term is, we refer to the sequence as an infinite sequence. So an infinite sequence is a function whose domain is a set of positive integers, as we discussed previously on the previous slide. And this will be the function values, the outputs. Or remember, if the input or the domain is the set of positive integers, then the outputs, which will be represented by numbers, those will be considered as the range of the sequence. And the terms of the sequence. The outputs. When the domain of the function consists of the first n positive integers only, meaning that n is the last term, like the nth, and we could also denote it by a sub n if we do know the last term, then your sequence is called to be finite. So finite if we know the last term, or if we know there exists a last term, and infinite if it doesn't have the last term, or we don't know where the ending is. So on occasion, it is convenient to begin the subscript as of the sequence with a 0. So it is not necessary to always start with the 1, with the first term. We could always, and sometimes it will be more convenient, you will see that in the following slides, to start with the number 0, with a 0 term. And so in this case, the domain, it includes 0 because that's actually one of the subscripts. So remember, the domain is going to be the little subscripts of the sequence, and they are integers, positive integers. In this case, we include 0. So here we have how are we going to write the terms of a sequence. And here the question for example 1 is to write the first 4 terms. And the sequence is here. And this is how we get the nth term. So if we need the first, the second, the third, the fourth, the fifth, the sixth, the 100th, we will use the same formula. And the only thing that we will be doing is replacing the n within the equation here and within the formula with the term that we're getting. So if we're getting the first term, then we will replace that n with a 1. Now if we're getting the second term, then we will be replacing, you can see the subscript here is a 2 because it's the second term. We will replace the n with the number 2. and so on. So let's go ahead and finish the work here. Well, let's see how we substituted for all of them. So for the third term, we have the subscript is a 3, and we have here a 3. Then for the fourth term, we do the same thing. Subscript is a 4. So then within the equation, we replace the n, the letter n, with a 4. Now let's go ahead and simplify. So following the order of operations, we have to multiply first. So 3 times 1 is 3. And then we subtract 2. So 3 minus 2 is equal to 1. Then we have 3 times 2, which is 6. 6 minus 2 is going to be 4. Next term will be 3 times 3, which is 9, minus 2 is equal to 7. And here 3 times 4 is 12, minus 2 is equal to 10. So those will be the first 4 terms of the sequence. And we could also list them this way. 1, comma, 4, comma, 7, comma, 10. And those will be the first 4. If we were asked to just find the third term, of course, it will just be the number 7. Or you could enter it such as a sub 3 is equal to 7. For WebAssign, you need to be careful and see if they already include, if they want you to enter your answer as an equation, or if they already included the subscript of the term. Like the a sub 3, and in that case you might just have to enter the number 7. So be careful on the way that you enter your answer while you're doing your homework on WebAssign. For example 1b, we're going to write again the first 4 terms of the sequence, and you could see that we already have the substitutions here, and we do have the formula for the nth term of the sequence. And you could see that the only part where the n, the letter n, appears is here in the exponent of -1. So what we're going to be doing is substituting on the first term. We will substitute that n with the number 1. On the second term, we substitute that n with the number 2, and so on. So third term, the exponent will be a 3. And for the fourth term, we will have the exponent being a 4. And also the subscript. So following the order of operations, we must do exponents before we can add. So in this case, I'm going to write the 3 so that I don't forget. Also, it's good to work from left to right. So now we say -1 to the power 1 is just simply -1. So this addition of 3 plus -1 is the same as saying 3 minus 1, which is 2. For the next one, the 3, we write that first so we don't forget about it. And then -1 squared is going to be -1 times -1. So remember that when you multiply two negative numbers, they turn into positive. The product will be positive. So this becomes 3 plus 1, which is 4. For the next term, it's going to be 3 plus -1 to the third power. So in this case, we have -1 multiplying by itself 3 times. And in this case, from the first 2 -1s, you get a positive 1. But then positive 1 times the third -1 is going to give us -1. So this turns into 3 minus 1. And this will be equal to 2. For the next problem, we're going to have 3 plus -1 to the fourth power. So if we have the product of -1 4 times by itself, it will be from the first 2, we will get a positive 1. And then from the other 2 -1s, we also get a positive 1. So if you multiply positive 1 times positive 1, you definitely get a positive 1. So for this term, we're going to have 3 plus 1, and that will equal to 4. So if we were to list our 4 terms for the sequence, they will be, our first 4 terms, they will be 2, 4, 2, 4. And this is something you can notice the pattern. It's going to be 2, 4, 2, 4. And that is because of the exponent of the negative number. So whenever you have a negative number raised to a certain exponent, if that exponent is odd, like in these two cases, here and here, the answer will be negative. In this case, -1. And if you have an exponent that is even, like a 2 or a 4, then the product of that is going to be +1. You may also be asked to write your terms by using the actual I guess symbol to denote them. So a sub 1 is equal to 2, a sub 2 is equal to 4, a sub 3 is equal to 2, and a sub 4 is equal to 4. So that would be another way they might want you to enter the answer, or maybe just the number separated by commas. Simply listing the first few terms is not sufficient to define a unique sequence. The nth term must be given. So we need to have that formula or that model that will tell us how to obtain all of the terms. To see this, consider the following sequences, both of which have the same first 3 terms. So we can look at sequence number 1 and sequence number 2. And you can see the first term for both is 1/2, the second term is 1/4, and the third term is 1/8. And the same thing happens there. However, the formula for the nth term happens to be different, very different, in fact. And so that's why we need to be given the formula for the nth term. You could see here that for the fourth term of the sequence, this one happens to be 1/16, and for the other one is 1/15. So they are different, even though the first 3 terms were the same. Some sequences are defined recursively. To define a sequence recursively, you need to be given one or more of the first few terms. All other terms of a sequence are then defined using previous terms. So for example, the Fibonacci sequence for that sequence, we have that the first term is equal to 1 and the second term is equal to 1 as well. Now from there, the definition is that let's say the nth term is going to be given by the addition of the term before n, which we could call n minus 1, and plus the term before this one. So it will be 2 before n. So it will be n minus 2 for not 1, but 2 for the subscript. So for example, if I want to find the third term, a sub 3, we will use the term previous to a sub 3, which will be a sub 2, and also the term previous to it, right before a sub 2, which will be a sub 1. So in this case, we're able to find a sub 3 by adding the second term, which is here 1, plus the first term, which is also 1. And so a sub 3 is equal to 2. So if I want to find a sub 4, it will be equal to a sub 3, the one before, and then the one that is 2 terms before it, a sub 2, before this one. So in this case, a sub 3 is 2, and a sub 2 is 1 from here. So this will be equal to 3. Now if I want to find a sub 5, it will be the previous 2 terms, so a sub 4 plus a sub 3. And with that, we will get 3 plus 2, which is equal to 5. And so here, if we wanted to list the first 5 Fibonacci numbers, it will be 1, 1, 2, 3, and 5. And let's say I want to list another two more. So the next one is going to be the addition of 3 plus 5, which will be not 7, but 8, sorry. And then the next one will be the addition of 5 plus 8, which will be 13. And this is actually an infinite sequence. Um, it could, yeah, just like the set of real numbers. It's infinite. But it is recursive because to get one of the terms, you need the previous two. For example, to get the 13, we needed the previous two terms. And so that's an example of a recursive sequence. But notice how we had to be given the first two of those terms. And this is actually a very famous sequence. And it's kind of interesting because the numbers that you see here, they actually appear in nature, not like just the number written down, but they appear, for example, the way that petals and flowers, especially sunflowers, are arranged. They go in a circle and you have more than one layer. And so you could see how for some types of sunflowers, they might have like, I don't know, 8 petals and the inner circle and then they might have like another layer that has 13 and then the other layer will be 8 plus 13, so that is 21. And so they do happen. If you're bored, feel free to Google examples of Fibonacci numbers in nature, and you'll be pretty impressed. Also in pine cones, they do appear. Okay, so the next objective is to get you familiar with factorial notation. Some very important sequences in mathematics involve terms that are defined with special types of products called factorial. Also, I know that some of you already know that in this chapter, we're going to be looking at probability. And before we get to probability, we're going to look at certain theorems. One of those will be the binomial theorem, but we'll also will look at how to find combinations and permutations. And so for that, we need to be very, very familiar and know how to use the operation of factorial or the factorial operator. So you could see here the exclamation sign, and it has nothing to do with the meaning it has in English. It's not an excited N. What it means is N factorial. That is exactly how we read it, N factorial. And so what that means is that you will calculate the products of all the numbers that starting with 1, and not all the numbers, I should say all the integers, positive integers, starting with 1 and then consecutive integers, so 1, 2, 3, 4, 5, 6, 7, until we get to n. So for example, let's pretend that n was, let's say a 7. So then 7 factorial will be the product of 1 times 2 times 3 times 4 times 5 times 6 and times 7. So because I'm saying that n equals 7, this is representing the last term, the n, and the 6 is actually representing the number before n. So if it's before n, it makes sense that we call it n minus 1, like that. So the 5, by logic, it will be n minus 2, and so on until we get to 1. So that is an example for 7 factorial. So by definition, well, it is pretty obvious that 1 factorial is just 1 because it will just be the product of 1 times nothing else, just 1. For 0, it's a little trivial, but just take my word for it. Don't ask me why because I don't think I could explain it very well. But by definition, we will just take it like it is. 0 factorial is equal to 1. Don't question it. If you are very curious, feel free to Google it. There are some proofs that you could find online. But yes, 0 factorial is 1, 1 factorial is 1. Now, for 2 factorial, we have it here. It is 1 times 2, so it's equal to 2. For 3 factorial, we have 1 times 2 times 3, so that is equal to 6. 4 factorial, we have 1 times 2, then 2 times 3, then 3 times 4. Or we could say 1 times 2 is 2, times 3 is 6, and then 6 times 4 is 24. So if we wanted to find 5 factorial, it will be the product of 1 times 2 times 3 times 4 times 5. And that will be equal to 120. Another way that I could write 5 factorial is by using all these numbers that you could see. They're repeating because we always start with 1 and then 2 and then 3 and so on, consecutive integers. So instead of me writing all this 1 times 2 times 3 times 4, I could simply write 4 factorial. And then the next number times 5. So using the same idea, instead of, let's say, writing 4 factorial, I could say, you notice that here the first 3 numbers are 1 times 2 times 3, the first factors. And we could also see the same factors here, 1 times 2 times 3, and that will be the same as saying 3 factorial. So I can put my 3 factorial here. And then what else do I need? Times 4. And that will give me the same thing because 3 factorial is 6. 6 times 4 is 24. And so this is just a little trick that we will be using whenever we need to do some operations with factorial. So for example, if we have, let's say 10 factorial here, and then we have, let's say 9 factorial. So if I expand, the 10 factorial will be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. And for 10 factorial, I'm sorry, for 9 factorial, it will be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times, times 9. That was it. So you notice that we can cancel the 1s, the 2s, the 3s, because everything is just multiplying their factors, so we are allowed to do that. Or we could just say this whole thing is the same as this whole thing on the bottom, so canceling them, it equals to 1. So we are just left with 10. Now, another way to look at this problem is to save a lot of work. We could have 10 factorial over 9 factorial. And so instead of writing this whole expansion, we could just say 9 factorial on the numerator, 9 factorial on the denominator. But since this one is a 10 factorial, we're still missing the times 10. And so that's the way we can save a lot. That's the way we could save a lot of work. And then we get the same answer. The answer is 10. So this is why it's going to be important for you to get familiar with this type of operations. Now, sometimes factorials follow the same conventions for order of operations as do exponents. So remember, order of operations, we have parentheses, and this includes brackets, and it also includes fraction bars or absolute value. Then we do have exponents, and so we're going to put factorials in the same category. Then, of course, as multiplication or division, they have the same order of importance. You don't need to multiply before you divide. You do what's first on the left, from left to right. And then we have addition and subtraction, same rule, same order, but you do what's first on the left, from left to right. So factorials, they're going to be placed here in the same order of exponents. So for example here, for this expression, instead of saying the factorial applies to the 2 and applies to n, in reality it's only applying to n, like that. So what that means is that 2 is just an outside factor of this operation. It has nothing to do with the factorial. Then for n factorial, as we saw in the previous definitions, we start with 1, and then we continue going down by one integer and multiplying, or going up. So it will be 1 times 2 times 3 times 4 times 5, all the way until you get to n. N could be a 5, n could be a 6, we don't know what it is. N could be 100. But just knowing that there is a last term, that tells me that it will be a finite sequence. And of course the ellipses here, the 3 dots, that indicates that we don't know how many terms are in between, but the pattern is the same. We have consecutive integers. Now, the other one, you can see here on the bottom, this one does have parentheses, so then the factorial is actually applied to the whole sequence. But for any type of factorial, we always start with the 1. And then we go 1 up, 1 plus 1 integer, and then 1, 2, 3, 4, so consecutive positive integers all the way to 2n. So that will be the last term in this case. So notice the difference when you do have parentheses and when you don't have parentheses. Okay, so we have here the nth term, right, for the sequence, and we're being asked to find the first 5 terms. However, I want you to notice how we are going to call the first term, actually they're calling it the 0th term. I don't really like that, but let's just go with it. But what they mean is we're finding a sub 0. Then for the first term, we're finding a sub 1, a sub 2, a sub 3, and a sub 4. So recall that the first term could have a subscript of a 1, but it could also have a subscript of a 0. And this is just, for convenience. So we're going to take the formula that we have here to define our nth term, and we're going to replace, for every n that you see on your formula, we're going to replace that with the subscript that we have. So to find the 0th term, I'm going to make some lines here to divide my work. So to find the first term, the 0 term, I should call it, we're going to have 2 to the power 0 divided by 0 factorial. Remember, we had to substitute the exponent and also the number here that we're taking the factorial from. And so that means that a sub 0 is going to equal to 2 to the power 0 is equal to 1. And by definition, any number to the power 0 is equal to 1, except for 0. If you have something like 0 over 0, that is undefined. But any other number or term, it will work. By default, it's just equal to 1 if the exponent is 0. And 0 factorial, by the previous couple of slides, by definition, we learned that 0 factorial is just defined as 1. So you get 1 over 1, so that means that a sub 0 is equal to 1. Now for the first term, this is going to be 2 to the power 1 divided by 1 factorial. And in this case, we replace the exponent in the denominator before the factorial sign with a 1. So 2 to the power 1 is 2, and 1 factorial by definition is equal to 1. And so 2 over 1, that means is equal to 2. For the second term, which in reality is our third term, but whatever, a sub 2, that will be 2 to the power 2 over 2 factorial. So just like we have here, we are replacing our exponent with a 2 and our factorial, the number for the factorial as well. So simplifying this, we're going to get 2 to the power 2 is 4. And 2 factorial is the same as 2 times 1, which is 2. So that means that a sub 2 is equal to 2. Next term, we're going to have 2 to the power 3 over 3 factorial. Again, we replace the exponent and the number down here because we're doing the same thing for every time we have an n. So 2 to the power 3 is the same as 2 times 2 times 2. That's equal to 8. And 3 factorial is going to be 3 times 2 times 1, or in reverse, 1 times 2 times 3, which is 6. Now here we cannot divide and get an integer. However, we could simplify it. We could take half of 8, which is 4, and then half of 6, which is 3. Now on the next one, we will have 2 to the power 4 over 4 factorial. In this case, 2 to the power 4 is equal to 16, and then 4 factorial is equal to 24. So in this case, we could divide both numbers. We could divide them by 2, or we could divide them by 4, or we could actually divide them by 8. So 16 divided by 8 is a 2, and 24 divided by 8 is a 3. So that will be the reduced form for that sequence. And of course, you could always check your work. You notice how here we have 2 and 2 for a sub 1 and a sub 2. So I'm just going to check it one more time. 4 over 2. Yeah, it is correct. So don't be afraid if you get two terms that are the same. Sometimes it does happen. But it's a good idea to still check your work. So when working with fractions involving factorials, you will often be able to reduce the fractions to simplify the computations, as I showed you earlier. So let me give you another example. Let's say that we have 8 factorial, well, 8 factorial here. And then we have on the bottom, let's say, let's say 6 minus 2, and then factorial. Well, we know that 8 factorial will be 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. And for the bottom, the first thing we need to do is subtract what's inside the parentheses, because parentheses, according to the order of operations, parentheses, it has the first order. We need to take care of that before factorials, which are in the same order as exponentials. So 6 minus 2 is equal to 4. So this is in reality 8 factorial over 4 factorial. And so 4 factorial is going to be 1 times 2 times 3 times 4. So what we know from here is that the first 4 terms are the same, right? And so we could say they do cancel out because they equal a 1. And so the ending product will be 5 times 6 times 7 and then times 8. So 5 times 6 times 7 times 8, and that will be equal to 1,680. I'm going to check one more time. 5 times 6 times 7 times 8. Yes, it is correct. Now, if we do it this way, remember first I had to subtract the number, so that's why I have 4 factorial. In this case, I know that the smallest number from 8 and 4 is 4, so I'm just going to use 4 factorial here. And for 8 factorial, I'm going to use what I already have here because I'm hoping to cancel it. So I'm going to have 4 factorial, but remember that only covers the numbers from 1 to 4. So to get to 8 factorial, I still need to multiply times 5, times 6, times 7, and times 8. And so in that case, we could say that 4 factorial cancels with 4 factorial, and we just have 5 times 6 times 7 times 8, which is 1,680. So yeah, those are very useful things to know. Let's do one with letters. So if we were to have n factorial here, and then here I have n minus 1 factorial. So let's think about it. Which one is smaller? Is n bigger than n minus 1? Yes. So the smallest is n minus 1. So then I'm going to choose to use n minus 1 in parentheses factorial here. And that means that is the same as saying 1 times 2 times 3. And then we can use dot, 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 and then use n minus 1. That will be the last term that is multiplying. Now for the top, that is n factorial. We already know that. So that is actually 1 times 2 times 3 times 4, and then dot, 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 my n minus 1, and then times n. Remember, n minus 1 is the term that is right before n in the consecutive positive integers. So you could see how from 1 to n minus 1, those products are the same. So we could cancel that out, and our answer would simply be n. Now, how would I write it here? Well, I would say n minus 1 factorial, because I know they have that in common. And then I'm still multiplying by n, because I had to get all the way to n, not only stop at n minus 1. So from here, we can cancel a minus 1 factorial with n minus 1 factorial, and our answer is simply n. So we have here the summation notation. And the symbol that you see here, it is the letter sigma, and indicates summation or addition. So this is a way to shorten a sequence or a question, because we are given the formula, and we are also given the first term that we will start with. And I know we see an I, but don't get confused with imaginary numbers. I know we just finished section 6.5, the trigonometric form of a complex number. So this I has nothing to do with the other I, or with the I that we saw with vectors, with the I and J components. If you don't know what I'm talking about, then you need to go back and study. Anyways, this I just indicates the subscript of your sequence, of your term. And then the number on top, it indicates the last one. So first and last. Notice how on example B, our first term is the third term, because we have k equals 3. That's another thing. The letter could be whatever you want. It could be n, it could be k, it could be I. Those are the most commonly used. So the first term will be the third, and the last term will be the sixth term. So in this case is the fifth. Okay, so let's go ahead and work that out. And the difference with the sequence is that now with the sequence we just had commas in between the numbers. Now we're gonna add the numbers. So first we have to find the terms. So the first term will be 3 times 1, because that's the index here. The next one will be consecutive integers, so it will be 3 times 2. Then 3 times 3, then 3 times 4, and then 3 times 5. So from here, we're going to go ahead and multiply. So 3 plus 6 plus 9 plus 12 and plus 15. And after adding the numbers, we get 45. So that will be the answer to the question. So we're not just listing the terms, we're actually adding them. For the next summation, we start with the third term. So we're going to use 1 plus 3 square parentheses. That's the third one. Then the fourth one is going to be 1 plus 4 square and close parentheses. Then we will have 1 plus 5 square, close parentheses. And we need one more because the last one needs to be our sixth term. So this will be 1 plus 6 square, close parentheses. So remember, the last term was the sixth term. So in this case, we need to take care of the exponents first. So the third term will be 1 plus 9. Then we will have 1 plus 4 square, which is 16. Then we will have 1 plus 5 square, which is 25. And then we will have 1 plus 6 square, which is 36. Now we're going to go ahead and add the terms inside the numbers, inside the parentheses. And that will be 10 plus 17 plus 26 and plus 37. And the answer is 90. Now moving on to part C, we could see the factorial is there. And we could see that the first term is going to be the 0 term. So, and the last one will be the 8th term. So we start with 1 over 0 factorial. Then we will have 1, not equal, but plus. One over 1 factorial. Then we will have 1 over 2 factorial, 1 over 3 factorial, 1 over 4 factorial, 1, I put equal again, sorry. 1 over 5 factorial, 1 over 6 factorial, 1 over 7 factorial, and finally 1 over 8 factorial. So you could see that the for 1 over 0 factorial is the same as 1 over 1. So it reduces into a 1. The next one will be 1 over 1. So it's also a 1. The next one will be 2 factorial is equal to 2. So it's 1/2. 3 factorial is equal to 6. So we have 1 over 6. 4 factorial is equal to 24. So it's 1 over 24. 5 factorial is 120, so we have 1 over 120. 6 factorial is equal to 720, so we have 1 over 720. 7 factorial is 5040, so we have 1 over 5040. And finally, 8 factorial is equal to 40,320, so we have 1 over that number. And if we add all those fractions, if you could put them in the calculator, you will see that you get approximately this number, 2.71828. Now that number, you might remember it from your previous class, Pre-Cal 1. It is the approximation for the irrational number e. And you looked at that with exponential, in the chapter of exponential functions, exponential and logarithmic functions. So that is a way to approximate it. There's another way to approximate e by taking limits. And it can be shown that it has more terms of the sequence whose nth term is 1 over n factorial. So the more terms that you add, the larger n is, you will have more fractions to be added. And so the sum, the addition, will become closer and closer to what e is. For our class, we are going to use, since you can use your calculator, you will use the button that contains e to the power x if it's necessary. And also, I want to point out that it's the second most famous irrational number. The most famous irrational is pi. So some of the properties with summation, we have that if you're adding constants and you add those constants n times, then it will be the same as the product of that constant times the number of times. So Cn. So for example, if you had a summation, let's say we start with k equals 1. Well, this is very ugly. And then our last term, let's say, is 4. And our constant is going to be 10. So we need to add the first term, which will be 10. The second term, which will also be 10. The third term will be 10, and the fourth term will also be 10. Why are they all 10s? Well, because there's no n here that we can substitute. The sequence or the summation only has a constant. So we have 10 added 4 times. And so that's the same as us saying, we look at what's the last number here, and it could have been just 4 times number 10. And that is 40, which is the same as 40 over here. So similarly, if you have a constant and then you actually have like some formula to find your terms, then you could always factor out that constant, as you could see here, and then carry out your sum like we did on the previous examples. And then at the end, multiply your result times the constant. So you will get the same thing, as if you were to have the constant with each term as you're adding. So we could also have, if we have the summation of two different terms, here they're indicated by A and B. So it will be the same as if you take the sum of the first terms and then you add, and then you take the sum of the second terms and then you add them all together. So you could either do either way, like we have here on this side left or on the right side. And then that property is the same for subtraction. So you could either find each term like that and then put them all together with the addition, or you may break it into two summations and then do that operation first, and then at the end subtract the two results. Now we're gonna move to, well, actually we already started, and we do, when we add the terms, the sum of those terms is called, the sum is called a series. And this is something that will help you out tremendously if you do happen to take Calculus 2. It is a part of that course. So we say sometimes, remember how we started discussing finite and infinite? So finite, it has an end, just like the first three letters, fin, which means the end. And so finite series have the last term, which in this case is denoted by a sub n. Now there are others, the infinite, they have no end, and those in the summation notation will be indicated with the infinity symbol. Or if we expand them, it will be indicated by the 3 dots at the end. It just means that it keeps going. So therefore the domain is infinite. And also the number of terms. So we're going to go ahead and find the, well, let's go back actually. Now, we could always make a infinite series finite if we kind of like determine how many terms we want to add. So for example, if I have an infinite sequence and then I want to add, let's say, the first 3 terms only the first three, then I will call that an nth partial sum, or it will be the third partial sum of this infinite sequence. And so that is what we're going to do on the next one, on the next example. And so here we have the series is 3 over 10 to the power I. And first, we're going to find the third partial sum. So the first three terms. And that's why we start with a 1 and we end with a 3, with the third one. So we have here 3 to the, and notice how here the only thing that I am substituting is the exponent of the number 10. So in this case, the I. So the first term, we substitute that with a 1, second term with a 2, third term with a 3. So if I expand this one, it will be equal to 3 over 10. The next one will be 3 over 100. And the next one will be 3 over 1,000. Because 10 squared is like 10 times 10, so it's 100. And 10 to the third power is 10 times 10 times 10, which is 1,000. Now, if I wanted to write this as decimals, it will be equal to 3 over 10 is the same as 3 tenths, so 0.3. The next fraction is 3 hundredths, so it will be 0.3, no, another 0, and then 3. The next one will be 3 thousandths, so it will be 0.003. And if we add all those numbers together, those three numbers, we will get 0.333. And in fact, this is an approximation of 1/3. So 1/3, it's approximately 0.333 if we were to round it to the nearest thousandth. Now for the next one, for this, the sum of the series, we will have, this will be an infinite series, and because we have the last term being infinite. So, and we also have this part here. So just the same way that we did the other sum, you could see here that we replace the exponents, and if I use the same idea, and that actually happens to be 1/3. There is a way that we could enter this on the calculator. I will be showing you that as we move on with the chapter. But yes, it is 1/3. And in fact, this is an example of something called a geometric sequence, which we will be working with in section 9.3. Okay, so another application of sequences or series will be in business and science. And this example shows you one of those applications. And it says an investor deposits 5,000 in an account that earns 3% interest compounded quarterly. The balance in the account after n quarters is given by the equation that you see here. for n is equal to 0, 1, 2, and so on. So we have here the deposit or the principal is 5,000. And then the 3% interest converted into a decimal is 0.03. Then because the interest is compounded quarterly, that means that here this is equal to 4. And for us to find the balance after a certain number of quarters, we will be substituting the exponent that we see here for n with the numbers 0, 1, and 2. So, and so on, because we don't know what n is. In fact, we could just consider n to be the last term here. So for part A, they want us to write the first 3 terms of the sequence. And then for part B, we're actually going to be finding the balance in the account after 10 years by computing the 40th term of the sequence. Now, the original deposit, which will be the quarter 0 when the investment was made. So you could see how here we have the subscript 0. We also replace n with a 0. Then for after the first quarter, we have a sub 1, so we replace n with a 1. And all the other parts remain constant. So the 2, a 2, and then here for the 40th term, we will replace that n with a 40. And so I already have I left the answers here from the PowerPoint, but I want to show you how to enter this on your calculator. So it will be 5,000, open parentheses, then you will enter a 1, then plus, and then for this function here, for this fraction, we're going to put it in parentheses. So it will be 0.03, then you will press the key for division, and then 4. Then you need to close your parentheses just to make sure that the fraction stays together. Then you close it again to close this first parentheses. And then you use the key that has the exponent symbol, and then you enter 0. And of course you press enter. So for the 40th term, and I would like for you to practice on your calculator and see if you get the same numbers. Usually if we're talking about money, we want those terms to be rounded to the nearest hundredth because we want them to resemble cents. So in this case, it will be parentheses 1 plus parentheses 0.03 divided by 4, close parentheses, close it one more time, to the power 40. Notice how this parentheses keep my fraction together, and then the last parentheses is the one closing the one in front of the number 1. So this is the end of the video.